This is the second video on the notes for 8.2, graphing of exponential functions. So we're starting with example 4. In our previous examples, we looked at shifting the graph up and down and left and right. Now we're going to see what happens when we make the exponent negative. So we have b to the negative x as our general form. So we have two different equations here. We have 2 to the negative x and 3 to the negative x. Let's start with 2 to the negative 0, so our x value is 0. Well, negative 0 is just 0, so we have 2 to the 0, which is 1. Anything to the 0 power is always 1. Same thing with 3 to the negative 0, that is going to be 1. Then we have 2 to the negative 1, which is 1/2, because the negative exponent puts the 2 in the denominator. We have 2 to the negative 2, 1 over 2 squared, it's a square, which is 1/4. We have 3 to the negative 1, which is 1/3, 3 to the negative 2, which is 1/9. The third power you probably don't need to do, but we can do it. 2 to the negative 3 is 1/8, 3 to the negative 3 is 1/27. This should all be non-calculator. Okay, now we have 2 to the negative x, and x is negative 1. So this is really 2 to the 1, which is just 2. 3 to the negative 1 is also 3 to the first power, which is 3. Then we have 2 to the negative, plug in negative 2. So 2 squared, which is 4. And we have 3 to the negative 2, which is 9. Okay, so we can graph these. I'm going to move to the next page on the iPad, but you have a graph right here where you can plot these points. So I'm going to do 2 to the negative x in green. At negative 2, 2, 3, 4, my point is at 4. Negative 1, 2, 0, 1, and 1/2, 1/4, 1/8. I could also plot negative 3 if I wanted to. Negative 3, the output would be 8. So it would be right here. Okay, so I'm going to sketch that line. Whoop. So it would look something like that. It's hard to do with the stylus, but yep, something like that. Okay, so that is 2 to the negative x. Let's do 3 to the negative x in blue. So we still have a point at 0, 1, then negative 1, 3, negative 2, 9, should be up here, and positive 1, 1/3, 1/9, 1/27. All right. Put some arrows on that. Okay, so this was 3 to the negative x. So what happened to these graphs from the original? Well, the original graph would have been, would have looked like this, something like that. So what happened? Clearly it was reflected over the y-axis. Okay, let's go back and do some key features. So I'm just going to sketch a really rough graph here. Oops, keep that above the x-axis. Those are our two graphs. Okay, so key features. Domain, it's still all real numbers. Range, well, we still have everything above 0. So this is 0 to infinity. Key points we'll come back to in a second. Y-intercept, 0, 1 still. Increasing or decreasing? It is definitely decreasing as we move from left to right. horizontal asymptote, y equals 0. End behavior. As x goes to negative infinity, what is f of x doing? In our previous graphs, f of x was going to 0 as x went to negative infinity. But here, as we move to the left on the graph, these graphs are going up towards positive infinity. Then as x goes to positive infinity, what's happening to f of x? So as we move towards positive infinity, our graph is going towards 0. Okay, key points. Well, the y-intercept is still definitely a key point, so 0, 1 for both of these graphs. And then -1. So we have 0, 1. Our other original key point on a parent function is 1, b. But because this has been reflected, this is now -1, b. So -1, 2 or -1, 3. Okay. So how does the graph of b to the negative x compare to b to x? It has been, or we could say it is reflected over the y-axis. Okay, another key thing to note, these graphs are actually the same for b to the x when b is between 0 and 1. So if I went up here, 2 to the negative x is the same thing as 2 to the negative 1 raised to the power of x. Oops, there we go. 2 to the negative 1 is 1/2. So this graph is actually identical or equivalent to 1/2 to the x. So 2 to the negative x is the same thing as 1/2 to the x. This one would be equivalent to 1/3 to the x. So if our b value is between 0 and 1, it looks like a reflection. All right. On to the next kind of graph. Negative b to the x. So now the negative is out front and not in the exponent. So we have -2 to the -2 power. That's -1/4. -2 to the -1. Well, we've got a negative out front. 2 to the -1 is 1/2. -2 to the 0 is -1. -2 to the 1 is -2. -2 squared is -4. -2 to the 3rd is -8. All right, similarly, -3 to the -2 is going to be -1/9. Then -1/3, -1, -3, -9, -27. Okay, so let's get ready to graph that. Okay, -2 to the x. Let's start with 0, -1. We add 1, -2. 2, -4. 3, -8. 5, 6, 7, 8 down here. -1, -1/2. -2, -1/4. And we know it would just keep getting smaller. Okay, so that looks like something like this. So again, it's getting really close to the x-axis, but not crossing it, because there's no value that will make this -1/100 so small that it becomes 0. It's not possible. Oops. Okay, let's do -3 to the x. It's still a key point at 0, -1, then 1, -3, and 2, -9, which is going to be just off the screen here. Okay, -1, -1/3, -1/9, 1/27. Okay. So this is -3 to the x and -2 to the x. So let's go back and do some key attributes. Domain, still all real numbers. You can plug in any x value and get a y value out. The range, however, everything was below the x-axis. So the highest value is 0, and the lowest value, think about it, is -infinity for our lowest value and 0 for our highest. So this is going to be -infinity to 0. Y-intercept was 0, -1. Increasing or decreasing? Well, as we move left to right, we are definitely decreasing. Horizontal asymptote, y equals 0. End behavior, as x goes to -infinity, so as we move to the left, what's happening to f of x? It's headed towards 0. Then as x goes to +infinity, so as we move to the right, f of x is headed towards -infinity. Oop. -infinity. Key points. Well, our y-intercept is definitely 1. So in our original graph, it's 1, 0, but here it's become 0, -1 because of the negative in front of our base. And then we normally have 1, b as a key point. That's been negated, so it's instead of positive b, it's negative b. So in this graph on this previous page, we had a key point at 1, -2, so this is the 1, -b, and we had a key point at 1, -3. Okay, so how does the graph of y equals -b to the x compare to y equals b to the x? It has been reflected. So it's reflected over what line? Well, let's take a look. Oops. Normally the graph looks like this. So it's been reflected over the x-axis. All right, on to example 6. Now, I wasn't able to get example 6 to upload into this program, so I'm just going to use the white space here. In example 6, we're looking at, excuse me, at f of x equals a times b to the x plus k. We've already done the plus k. We know that moves things up and down. So what we're really looking at here is the a value. In your table, we have x values, and we have f of x equals 4 times 2 to the x, and g of x equals 8 times 2 to the x. I filled in the x values for us, so now let's start plugging things in. We have 4 times 2 to the -2. So we know 2 to the -2 is 1/4. So this is 4 times 1/4, which is 1. Then we have 4 times 2 to the -1. So that's 4 times 1/2, which is 2. 4 times 2 to the 0, well, we know 2 to the 0 is 1, so this is 4 times 1, which is 4. 4 times 2 to the 1, which is 4 times 2, which is 8. And 4 times 2 squared, which is 4 times 4, which is 16. Okay, so our key values, or values that we're going to plot, are 1, 2, 4, 8, and 16. For g of x, if we have 8 times 2 to the negative 2, we have 8 times 1/4, which is 2. 8 times 2 to the negative 1 is 8 times 1/2, which is 4. 8 times 2 to the 0, which is 8 times 1, or 8. 8 times 2 to the first, 8 times 2 is 16. 8 times 2 squared is 8 times 4, which is 32. So our y values are 2, 4, 8, 16, 32. Okay, so if this had just been 2 to the x, these values would have been 1/4, 1/2, 1, 2, and 4. So what's happened to those values? 1/4 became 1, 1/2 became 2, 1 became 4, etc. They've obviously been multiplied by 4. So let's think about what that's going to look like on your graph. So let's actually go to graphing this. So at -2, plot point at 1, and -1, 2, then 4, and 5, 6, 7, 8. Okay, and if I went to -3, this would be 1/2. All right, so it's going to look like, again, excuse that the stylus does not draw straight lines very well. It's going to look like that. The original graph, 2 to the x, looks like this. Just keep that above the x-axis. So what's happened to the graph? It's been stretched. This was 4 times 2 to the x. Let's add 8 times 2 to the x in there. At -2, has a point at 2. Then 4. And 8. And then it goes off the charts. Okay. So we can tell that this graph has been vertically stretched as well. So the points that were on the original get stretched up. You can see that they're getting stretched up significantly. So that's happening because we're multiplying by y. We're multiplying by 4 to our y value. Okay, the last thing is looking at not 2 to the x, but instead looking at 4 times 2 to the x plus 1. So what happens when we just add 1? So I'm going to take the numbers from over here and add 1. So 1 plus 1 is 2. 2 plus 1 is 3. 4 plus 1 is 5. 8 plus 1 is 9. 16 plus 1 is 17. That's going to be off the chart. But let's graph this in red. So we're taking these purple numbers and we're adding 1. So we have a point at -2, 2. -1, 3. 0, 5. 2, 3, 4, 5. 1, 9, which is up here. So we can see that this purple graph has just been shifted up 1. Okay, so let's go back and do key attributes. So domain for these graphs, still all real numbers. Range, the lowest value for any of them is 0, and it doesn't hit that value, so we use parentheses. key points. Well, in our normal graphs of 2 to the x or b to the x, we had 0, 1 as a y-intercept and 1, comma b. So what's happening to those? Well, 0, 1 is becoming 0, a times 1, or just a. So our graph is a times b to the x. And then 1b becomes 1a times b, because you have a times b to the first. Here you have a times b to the 0, and b to the 0 is just 1. So let's just change this so it just says a. Okay, so that's for a times b to the x. If we were doing a times b to the x plus k, our key points, instead of being 0, 1 or 0a, it now becomes 0. We know a times b to the 0 is just 1 plus k. So this is a plus k. And 1b becomes 1, comma a times b to the first plus k. So for the 4 times 2 to the x, let's do it specifically. For 4 times 2 to the x plus 1, our key points are 0, and then a plus k, so 4 plus 1 is 5, and 1, comma 4 times 2, which is 8, plus 1, which is 9. So those were the key points that we would want to use in a sketch. So, like this sketch. All right, other key features. We have the y-intercept, which we've already identified, 0, comma, a plus k. Or for this specific graph, 0, 5. Increasing or decreasing? We are definitely increasing. Horizontal asymptote. If we're doing y equals a b to the x, the horizontal asymptote is y equals 0. If we've got a times b to the x plus k, our horizontal asymptote is y equals k. And it occurred to me, I think I graphed something incorrectly here. When I graphed the red, I graphed our horizontal asymptote incorrectly. The red should approach 1 because everything has been moved up 1. So it is not approaching 0, unlike the other ones. Okay, so we just fixed that. For if you're adding k, the horizontal asymptote is k. End behavior. And we're going to do end behavior for both of these. So as x goes to negative infinity, what's happening to f of x? F of x is approaching k. Now if there's no k value, it's approaching 0. As x goes to positive infinity, what's happening to f of x? So as we move to the right, what's happening to f of x? It's going to infinity. Okay, so how does the a value affect the graph, and what does it represent? The a value vertically stretches the graph. So it affects the y values. And we can say if there is no k value, it represents an initial value. So if we just have y equals a times b to the x, When x is 0, you have y equals a times b to the 0, which is just a times 1, which is a. So this is going to give you an initial value at x equals 0. Okay, one more video to put it all together.